Okay, looks like we're doing the thing. It's happening again. Um, what's up, everyone? I am really excited to be doing this again. Um, if you don't know by now, I'm doing these streams every week at 10 in the morning Pacific time. Uh, really excited to be doing these, sharing the stuff I've learned over the years. I am trying to get out as much information as I possibly can to help people uh, either run distributed databases in production, usually Cassandra, or just talking about other stuff eventually. There's probably going to be a whole slew of topics that I talk about. So, like I said, really excited. Today I'm going to be talking about how to scale time series with Apache Cassandra. And I'm talking about massive scale. Like this isn't, we have 5 things that we're going to be tracking. We're talking about billions of records, absolutely massive data sets. So I'm just going to jump right into it. If you have any comments or anything, please leave them in the chat. I will try to answer everything as things go on. Yeah, please do. And we're off. Before we get going, though, one thing, a little bit of housekeeping. If you enjoy this session and you want to learn more and you want to do a hands-on session with me, I have opened up training. I've got a maximum of 20 spots. We're already 25% full. I'm going to be doing an 8-week training session starting in April. This is going to be a big deal. Definitely go to rustyrazorblade.com/training. Check out what we're going to be doing in the program. The goal here is to get folks up to the level that you would need to be if you wanted to work at like an Apple or a Netflix or any huge company that has massive deployments of Cassandra, really kind of big scale type problems. If you want to go from, an operator that's run a 3, 6, 9 node cluster, something like that, all the way up to running thousands of nodes in production, this is going to be a great course for you. Now, let's talk about our time series use case, and let's really kind of get an idea for what massive really means. These are the use cases that you'll hear about, like IoT, right? We've got Nest thermostats that are constantly reporting back sensor readings. They're constantly getting adjustments. You might be dealing with thousands or tens of thousands of readings per day. Autonomous vehicles, this is definitely going to be huge as things, as more and more companies roll out autonomous vehicles and they get more and more autonomous. The amount of sensor data that we're going to be collecting from each vehicle is huge, right? Each sensor is going to be reporting lots of readings back. This data needs to be stored somewhere. Cassandra is a really great place to do that. We've also, one of the areas that Cassandra is really strong right now, manufacturing, right? You have tons of manufacturing use cases. And then one that kind of, flew under the radar for me for a moment until I remembered it just a little while ago, like streaming media and social media. If we're tracking every single view, or we're tracking every single tweet, or every time someone plays a Taylor Swift song, these get into the hundreds of millions. And we need to be smart about how we store the data. If we store every single time that someone listened to a song, or every time they paused a movie, or any metadata around any type of single object that can get into the hundreds of millions, you're absolutely going to want to take advantage of this, because it is impractical not to. You'll run into some serious problems. So I'm going to talk a little bit about what I usually see. This is how most people will do time series. And it's okay if you're in this boat. This is a very common type of pattern. I'm going to show you the CQL for what this looks like. So we have a simple time series. We have our ID, which is going to be our partition key. Now that might be a sensor. It might be, the song that we're listening to. It might be something from the car or the car itself. Like it really depends on what your data model looks like. But the key here, the really interesting part is the clustering column where we have date created. And that can be a timestamp or it can be a time UID. Either one is fairly common. And then we have some payload. It doesn't have to be a text. It could be a blob or it could be a whole bunch of fields. It could be a map. There's a lot of things that it could be. But we're just going to put data here because I'll just assume that we have some type of serialized payload. So if you're looking at this and you've been using Cassandra for a while, you might already notice there's an opportunity here to improve things. We can do things a little bit better. So let's just show how we probably would actually see here. A lot of time series data is TTL. So people might put default time to live on here. Now, in this case, I've opted for a year. And you might also think to yourself, hey, we know by now, we've been using Cassandra for a little while. John, I've heard you talk before. We want to make sure that we use the right compaction strategy. Compaction strategy can make a really big difference. This is one of those things that you don't, if you're not careful about this, you can end up spending a lot of money. So you end up doubling the cost or tripling the cost of your cluster because you end up spending so much CPU time in compaction. So there's a really, really good compaction strategy called time window compaction strategy, written by a really smart guy named Jeff Jersa. This is basically allows us to only compact windows of data, and this is a fairly common pattern. But I'll be honest, it's not the best that we can do because we're putting everything into a single partition. And this is a huge mistake when you're dealing with massive time series. And the reason for that is because you end up with these unbounded partitions. So it seems like it's really great for the first month when you've got hundreds of megs of data or gigs of data. But as things get really big, like if you end up with partitions that are 10, 20, 30, 100 gigs in size, all of a sudden they become completely unmanageable. Streaming becomes a problem, repair becomes a problem. There's a whole slew of problems that we actually get as a result of this. Like I said, repairs, not great. TWCS, while it's awesome, isn't friendly for updates. So if you need to actually go back and let's say add additional information to your old data, not really a good use case for TWCS. There's also the pretty common issue that you can't change your TTL. So once you write your data with a TTL, you're not changing it at all, especially once you go outside that window. If you overwrite your stuff within the same window, not so bad because that data will be compacted together. But there is a problem where if all of a sudden you say, I want to go from 1 year retention to 3 years retention, or from 3 years retention down to 1 year retention, maybe you want to try and save some money. And going from 3 years to 1 year is a big deal. Like we're talking about potentially cutting the cost of your cluster by 66% in that case. If you get rid of 2/3 of your data, you can reduce your cluster size. So not being able to change your TTL, not great. And then there's another thing that most people aren't aware of, and it's pagination. Pagination is not particularly great with a single partition. We'll get into that in just a sec. First thing I mentioned was repairs, right? One of the issues with immutable time series data, or immutable after a certain point, is once you've repaired it, it's not going anywhere. So if you have everything kind of lumped into a table and all your data for a single thing is in a single partition, you end up repairing that same partition many times. And incremental repair was built to kind of solve this problem, but a lot of folks haven't moved to 4.0 yet. And also a lot of folks have been burned by incremental repair in the past. It was set as the default when it really wasn't ready. There was several bugs that existed with it before 4.0. And if you ever ran incremental repair with a cluster before 4.0, you may have run into this problem where all of a sudden you end up over streaming and now you've got like tons of tiny little SS tables and things get unstable. So from the perspective of repair, we generally kind of think about doing sub-range repair. If we're doing sub-range repair, then we're repairing already repaired data a lot. Like if you've got that 3 years that I was talking about and you're repairing every 10 days, then you're going to be repairing the same data 30 times per year times 3. Like, why repair data 90 times that's not changing? There's absolutely no good reason to do this. It's a waste of CPU. It puts extra pressure on your disk, puts extra pressure on the JVM, puts pressure on your network. It's expensive. You don't want to do this. Now, I also mentioned pagination. So this is the other problem. And this is a big one. And this one, I don't know if a lot of people know. So I'm going to walk you through how this works. Now, I'm going to take my face off for just a sec. So what we have at the top here is essentially a single, think about this as a single partition. And when you do your first query, you have something, there's a configurable setting in the driver that allows you to say how many rows you want to come back whenever you do a read, and that's your page size. By default, it's 5,000. I believe it's still 5,000. I don't think it's changed. It may have changed under me. Forgive me if I'm wrong, but I'm pretty sure that it's still 5,000. So you do a query and that 5,000 records come back to the user. Now, the other thing that comes back is something called a paging state. Now, I grabbed a little bit of the code out of the code base and put it in here for you. I hope you can see it. So that public class paging state says byte buffer partition key. So that tells you where, what partition key you were reading. And then there's something called a row mark. Now, the row mark is really, really interesting. I grabbed the class for it, but the thing that's the most relevant, that's most interesting here is the comment. So this comment says that the row mark is essentially the clustering column. It's the last clustering column in the in this result set. And so as you're iterating over this result set, when you get close to the end, the driver is going to go ahead and fetch the next page ahead of time. Now, here's the thing. It has to redo the entire query. This isn't a case where the result is fully materialized and you get to kind of efficiently read over it. You actually have to do kind of a lot of work. So what you're doing is you're fetching one page at a time and you're hitting whatever your RF is, let's say it's 3, you're hitting those same 3 nodes over and over, and you're reading one page at a time as you go down the partition. This is not particularly efficient. I don't really like it. And like I said, with an unbounded partition size, you really have no idea how much data that you have to read here. So our sequential pagination performance becomes a limiting factor in our application. We don't have the ability to just pull back a ton of data. If we ask the server for too much, it's actually not great on the server side. You end up with performance problems there. You really don't want to do that either. So you're kind of stuck in this like weird situation. So let's make an improvement. The first improvement that we're going to make is we're going to add a time component into the partition key. Now, the reason why this is so helpful, right, is because now we have multiple partitions for your time series. So we've accomplished a couple things here. One, and this is the big one, we've now made it so that a given partition is only as big as the amount of data that comes in for the time component that you specified. Now, in this example, I've picked something that's per day. This might be really useful if you're dealing with manufacturing, where you might have, let's say, reading every second, right? If you're storing time series once a second, now you're dealing with 86,000 plus records per day, assuming that your manufacturing is running all day. That can be problematic from a performance perspective. And I should note also, I'm not sure if I noticed this, I put I also put that day created in the partition key. So you see those parentheses around the ID and the day created. That means they're both part of the partition key. So each day is its own partition. And this is pretty helpful. My goal or my recommendation is to aim for between 1,000 to 10,000. I hope that's not confusing. 1,000 to 10,000 records per partition, because if we're paginating at 5,000 records at a time, you don't really have a great reason to go beyond a single page size. So that's kind of in the sweet spot of the amount of data that's going to come back. Right? We end up with a system that has multiple benefits. One, our older partitions become immutable, right? Instead of having one partition that's always changing over the course of the year, in the example that I provided, where we have a partition key that has a day component, now we have, in a year, we have one active partition for today, but every other partition for yesterday, the day before, etc., those are now immutable. And there's a really, really good reason to do that, which I'll get into in just a moment. We have less overhead from repair, because we no longer, once the data is repaired, it's no longer changing. And when you do have data that needs to be reconciled in a repair, the bigger the partitions, the more problematic it gets. Data gets better distributed. So I mentioned before that hotspot where you have tens or hundreds of gigs in a single partition. Instead of having a single partition that's like super hot, you end up distributing that data around the cluster. Now, when you expand your cluster, you're able to fully take advantage of the entire cluster. It's a nice little performance win, but it's also an operational win. So when I talk about this stuff, when I talk about performance, one of the things that's really important is that performance and reliability are tightly coupled. And those are all, and the other thing that's coupled that's really important is cost. So as we keep our performance, we keep our performance under control, we keep things optimized, we don't have to expand our cluster. And Cassandra clusters can get really expensive because you want to throw fast disks at it, you want to throw a lot of CPUs, great deal of memory. You can be talking about an expansion of a cluster might cost you hundreds of thousands of dollars. And if you have a systemic problem like incorrect time series or unoptimized time series spread throughout hundreds of clusters or even dozens of clusters, the cost can run into the millions just for not taking advantage of this. And if you look at what I've done here, all I've added is a single key into the partition key. I've added one column, and it didn't really change the data model that much, but the cost savings can be enormous. So with our fewer hotspots or better distribution, the other thing that we get out of this, or the last two things that we get out of this, is now we have the ability to query multiple partitions in parallel. So if we decide that we are going to query for 7 days worth of data, we issue 7 queries in parallel, and the driver will paginate over each of those at the same time. It's nice because we can pull all of our data back at once. We can spread that query or that request over the entire cluster effectively. If we hit 7 days and we've got our RF3, we can at most, we can take advantage of 21 nodes for this query. And we probably have a lot more time series that we're going to be querying than just one. So by distributing the queries throughout the cluster, it eliminates the hotspots, again, keeps our costs under control. And the last thing that I'm going to talk about with the advantage of this is it's very friendly for external cache. So in this scenario where we just talked to Cassandra, you might not think, hey, this is a big deal. But when we add a caching layer in, like Memcache, especially if we use ext store, where we can leverage an NVMe drive for extra storage, we can actually put a ton of data in each Memcache server. And it's way cheaper to run Memcache than it is to run Cassandra because you don't need a ton of cores. And Memcache can serve a lot more requests than Cassandra can. Memcache is effectively only taking blobs out of memory and returning them back to the user. Cassandra's doing a lot. So relatively, Cassandra does way more work and you get the same result out of it. So if you think about it as an opportunity to leverage Memcache instead of Cassandra, what you can do in the case where you wanted to read 7 days worth of data, 30 days worth of data, whatever, when you do your read out of Cassandra, you then store that in Memcache as a single object. So now when you want to do a read, you first look at Memcache, you ask for your data, and you're going to get data back for yesterday, the day before that, whatever it is. Let's say you did 7 days. 6 of your days are going to come out of cache, and only one of those queries is going to come out of Cassandra. And Memcache can handle hundreds of thousands of requests per second per instance, and it's cheaper to run. So it makes a lot of sense to shift as much work over to Memcache as you possibly can. So the next optimizations are now, we've already saved a ton of money by using this very, very simple change, by using parallel queries and by introducing Memcache. Like, this alone can allow us for our cluster to be a lot more performant, get used a lot less, and as a result, it's going to cost a lot less. So now I'm going to show you the next trick. This one is incredibly helpful. What we're going to want to do is use a table per block of time that we're going to be looking at. This one might be non-intuitive. If we, like, what's the advantage? Why would we possibly want to do that? And while we're at it, what happened to all of that other stuff that I had in there? Why is there no default TTL? Why is there no compaction strategy? Well, here's the thing. If we have our partition key, if we have a time component like day in our partition key, and then we put another time component in our tables, right? So this is this is the even better time series. You can see it's for 2024 and it's for this month, right? Whatever data we're writing for this month gets put in this table. Next month, we have a new table. Why would we do this? This seems kind of weird at first. Like, if you're looking at this and you're thinking about your application, you're like, oh, this is a lot. Like, I got to maintain more tables. I got to do more stuff. It's actually not a lot of work. Like, you're dealing with the same queries. You really just have kind of these templated prepared statements that can talk to the same schema across different tables. The reason why this is so great, and by the way, you're probably thinking, like I said, John, this is nuts. Like, where do our TTLs go? We love TTLs. Cassandra takes care of TTLs for us. Here's the good thing. Without a TTL component, now what we actually have are effectively dynamic TTLs. So if we decide that we have our data from last month and we don't want it anymore, we don't need it. All we do is we drop the table. We don't need Cassandra to compact that data and get rid of it. It's not necessary. We don't need really Cassandra to do anything. In fact, it just sits there. Our TTLs are now on demand. We can build our system where initially we say, you know what, there's 30 days. Who cares? We drop the table from the previous month. We create the new table for the next month. All good. And then someone goes, whoa, that's not cool. Legally, we can't do that. Oh, okay. We don't have the problem where we have all this previous data that we now have to try and think of a way to update the TTL for, which is honestly a real pain. You have to rewrite the whole thing. So all that we do is we just change the cron job. If could be cron, it could be Airflow, whatever you want, whatever you use to run scheduled jobs. You just change that thing to stop dropping your data that's only from last month, and now you leave it for 3 years, or maybe you go from 3 years to 1 year. This is really powerful. I can't state enough how useful this is. We implemented this in our at Netflix in our time series service. It was one of the things that allowed us to save a massive amount of money over previous time series implementations. So, okay, fine. Hopefully, I've convinced you. If I haven't convinced you, please let me know. Now we haven't listed compaction here, right? Why are we not talking about compaction? Well, the thing is, once you are now using tables as your time window. Now, remember, my old schema had a 30-day time window. And now our new schema has a 1 month time window, basically the same thing. What compaction strategy are we going to use? Well, now it's up to you. So TWCS will do size tiered compaction within a window. And then when you're out of that window, it just does a major and then leaves it alone. This is okay, but it can be problematic on certain systems. We did run into some performance problems when we were using slower EBS drives with a very, very heavily used time series database. You have the option to switch individual tables to leveled compaction, or you have the option to switch it back to size tiered and then do a major with the -S flag and have it split SS tables. And now every time you do a read out of that table, you only hit one SS table for any given partition key. So this is a huge benefit. You have a lot of control as an operator. It definitely can benefit you in a major way. So I really like doing this. I think this is very, very helpful. The other advantage here, and the biggest advantage, maybe not the biggest, but one of the other advantages that this has over using time window directly and controlling the windows by using tables, is that this is very, very friendly for repair, because now you've effectively implemented incremental repair without actually doing incremental repair. Those tables from the previous month, once that month is closed out and that table is like locked and is essentially immutable, it needs one repair, which you can do, and then you never need to repair it again. So you're only ever actively repairing the current window and one time for the previous window. So you close out the old window, cool, you put in some data. Now you're dealing with potentially gigabytes, like less than a terabyte, as opposed to trying to repair your entire data set. So if we had that case where we had 1 year of data, let's say, then every time you do a repair, you're repairing 1 year of data. That means you have to build a Merkle tree. That means you're exchanging SS tables. That means that when things go wrong, when repair detects an issue, you're streaming over potentially a ton of data. You don't have to do that anymore. You're at most dealing with 1 month of data at a time. It keeps your repair under control. It keeps your CPU usage to a minimum. It keeps your disk usage to a minimum. So if you're using, I mentioned EBS, there's a lot of people running Cassandra on EBS these days. If you're running Cassandra on EBS, this is going to massively help you. You do not want to push your IOPS on an EBS drive up to the point that you allocated for provision IOPS. Because once you do, the performance just drops off. They essentially shut you off. It's a quota. You're not reaching a limit gradually like you would with an instance, with an instance drive. You basically just hit a point where it can't do anymore. So for that second, and then things come back. So the performance on EBS is a lot different than local drive. So this being repair friendly and requiring you to look at less data is a humongous advantage for EBS and a massive cost savings, because with EBS, you're paying for the IOPS. As a result, what do we get out of this? One, it's easier to run dense nodes. Okay. If you think about the things that I've introduced, we've pushed a lot of our work over to Memcache for previous queries, because we don't need to read them out of Cassandra anymore. The previous day, it's immutable. It can be stored in Cassandra. It doesn't need to be read anymore. We're directing our CPU elsewhere, right? We're using the more efficient CPU on the Memcache side of things. We're not wasting CPU on repair, right? And we're not using as much CPU on compaction. So because of all this, we can put more data on each node. So if we double, triple, or quadruple the density of our node, if we go from 500 gigs to 2 terabytes or even to 5 terabytes, it becomes a lot more practical to run huge nodes, because now we can start to think about how much data can we put on each node versus how much can we query at any given time, because of all the operational overhead that comes along with really dense nodes. especially with newer versions of Cassandra where we have the option to do zero copy streaming. So this is another place where leveled compaction is really helpful. If we're using leveled compaction, we can take advantage of zero copy streaming. So now we've got 30 days worth of data that we're repairing. We're using zero copy streaming, and that 5 terabytes per node becomes a very, very doable operation. It's no longer super scary, right? And remember, you can always run the old. You can also run the major. Always run the major compaction on the older data if you choose to. Or if you don't want to keep your data in Cassandra, let's say that once you move past 30 days, these are now kind of more like analytics type queries. It actually makes a lot of sense to either roll up the data and either create a new table where we have all your data rolled up into a single aggregated view, and you just pull back that single payload. And remember, by limiting the number of rows per partition, we're going to keep things reasonably performing. Or we can just offload it out of Cassandra altogether and move it into an object store. Okay, that makes so if we put that, for example, in Parquet and move it to S3, now when we do analytics, we're querying S3 primarily, and maybe we still have to query a little bit of Cassandra data, but it's a lot cheaper to merge your data from S3 and Parquet and then query your most recent data out of Cassandra than it is to put all of your data in Cassandra. Cassandra is way more expensive than using an object store. It's not designed for analytics. It's designed to store the data that you need really fast access to. So if you can take your old data and you essentially have a workflow where you say, okay, for the previous month, I'm now going to take that previous month's data, I'm going to push it into S3 in Parquet format. Then when it's done, you drop the table. Well, instead of storing 12 months worth of data in Cassandra and querying it slowly in order to perform analytics, you actually get to query it really quickly out of the object store and use Cassandra as kind of more of a temporary housing for that data where we want access to the fast stuff. You need really, really quick access to the last 30 days worth of data, and everything else can be really slow. So streaming is faster. That reduces your overall cost in Cassandra by tenfold because you no longer have to worry about, you don't have to worry about storing it in Cassandra. So it's 10 times cheaper, which is great. That's exactly what you want. And of course, I have a slide where I basically explained all that. Like I said, less overhead on repair and compaction, just better data distribution. I forgot to mention, you also get better cache utilization on each Cassandra node. So when you have old data that's sitting there next to new data and you do a read, you're going to end up pulling a bunch of unrelated data into memory, potentially. And it's kind of a waste. You don't need that in your page cache. That results in more page cache churn. Page cache churn actually has a fairly high CPU overhead if you're doing enough of it. So this is more cache friendly. So your individual Cassandra node is going to be a lot friendlier. Because you're not recompacting the same data multiple times. Remember, every time this you might know this, but every time you run compaction, that data is being pulled into memory and potentially evicting other data. So by basically isolating each month or each day or whatever strategy that you're going to be using here, it means that we're recompacting old data less frequently, and you end up getting a huge performance win because your newest data is the thing that stays in cache. And I can't stress this enough. I always recommend, from an application perspective, pairing Cassandra with Memcache. If you have data where you're doing where it's cacheable, then it's a great solution. It's not a great solution if your data is not cacheable. And time series use cases, because they typically are write heavy, it's hard to optimize them for cache when you are not using this strategy, because you have these mutable partitions. It's just not great. So you end up being able to run potentially less data in Cassandra, but for the data that remains in Cassandra, now you have denser nodes, right? So you end up with massive cost savings. And at Netflix, we were able to save 90% by using these strategies. It is incredibly helpful. So hopefully that was helpful. I'm not seeing any comments right now. I love massive scale time series. Thank you very much. And amazing topic. Look forward to this. Thank you. Next week, I'm going to be talking about profiling Java applications with the async profiler. I've written a little bit about this before. If you're interested in reading about it in advance, I have a blog post about the topic. But the async profiler is really, really cool. And if you if you are interested in kind of getting to the bottom of performance problems in Java applications, it's the best. It's the best solution. It's not a solution for distributed systems. That's more of like an open tracing thing, and I may or open telemetry. I may touch on that in a little bit. But it's really, really good if you're looking on a single server. Can you talk a little about converting existing SS table into formats into other formats like Parquet? Yes, absolutely. Great question. So there are two options here. Three options. One is you just kind of naively read everything. You just read everything using the Java driver. That doesn't really work at scale. That works at small scale, but it doesn't work at massive scale where you might have a really huge cluster. Usually, I would advise people, and I am going to advise that you use Spark for this type of problem. Spark is really great at handling large data sets. You have two options within Spark. You can either use the DataStax connector, which goes through the front door. The problem with this is reading data out of Cassandra through the front door typically requires setting up another analytics data center. And because it can be so disruptive to the main application. And so a lot of folks basically like to have workload isolation. But this effectively can double the cost of your cluster if you're setting up an exact duplicate data center. And a lot of the time, like if you're only moving data out once a month, it can be kind of wasteful to run a second data center just for that purpose. You are much better off. Well, if you can, and this is something that's out there and it's under development. I haven't seen this used outside of Apple, but there's a project where we have a Cassandra Analytics library. So the Cassandra, it's either called Cassandra Analytics or Cassandra Bulk Analytics. And what it is effectively it works with the Cassandra sidecar to do zero copy streaming of SS tables to Spark, and then provides a mechanism where you can read SS tables directly. There's also a bulk writer. The thing is that it's pretty new. It's under development. I don't know a lot of folks using it. So it can, if you're expecting something that's kind of like we just drop it in, you're not going to be there. Like you probably will need to dig into the sidecar. If folks out there are interested in doing something like this, this is something I'd be more than happy to help with. This would be a really fun project to work on. So if you're looking for like long term, this is probably is going to be the best solution is to be able to use that analytics library with the sidecar, put minimal overhead on Cassandra itself, no extra pressure on the JVM, as long as you have the available resources through CPU and disk. And because it uses zero copy streaming, it's a lot less overhead than reading through Cassandra directly. Then you can probably get away with running it in the same data center. So this is a thing that will allow you to cut your cost in half. So if you're spending millions of dollars to run multiple data centers just for the sake of doing analytics, this is probably a project that you're going to want to work on. And like I said, this is definitely within my wheelhouse. I actually am I committed a lot of the original code into the sidecar back when I was working at Apple. So I definitely would recommend going down that path as a long-term solution. And the throughput that you can get out of it, it's not just cheaper to run. The throughput is significantly improved. So, you're actually going to be able to do analytics on your Cassandra data way faster than you would be able to do if you use the DataStax connector, which is still a good project. I'm not I don't want to sound like I don't like the project. It's just that the bulk analytics library is, it makes a lot more sense for a lot more use cases. So with that, I'm at 40 minutes. It looks like we are done. Yep, we are done. So I'm going to wrap things up now. Thank you very much for joining. I appreciate the questions, comments. If you enjoyed this, please, do the whole thing. Whole like and subscribe thing. I hate asking for that, but I definitely want to get a lot of attention on this stuff. I want to put out a lot of helpful content, and this is going to help me make that happen. So if you like it, share this with your friends. All right. Well, thank you very much. Have a great day, everyone.